All right, so last part of section 11.2 we're going to look at is, it's still on series, except now we're going to look at an infinite series. All right, so kind of weird question. Can you add up an infinite amount of numbers and get an answer? Well, it depends. Sometimes you can, sometimes you can't. And we'll look at both cases. So as I said earlier, there are some types of series that when you add up an infinite amount of terms, you actually get an answer. Let's think about an arithmetic sequence for a second. How do you get from one term to the next in an arithmetic sequence? Yeah?
You add a number.
You add. Okay, you add to get from one term to the next. So, do you think in an arithmetic sequence, well, what happens to the terms? As you keep adding a number, the terms in the sequence just get what?
Either bigger or smaller. It's like a negative number.
Right, they either get bigger and bigger and head towards infinity, or they get smaller and smaller and head towards negative infinity. So, in an arithmetic sequence, if you add up an infinite amount of terms, it's never actually going to approach anything. All right, so yeah, if you add up infinitely many terms in an arithmetic sequence, it's never going to add up to anything, because the terms in an arithmetic sequence are always just getting bigger and bigger and bigger, or smaller and smaller and smaller towards negative infinity forever. So the idea of an infinite series doesn't really apply to an arithmetic sequence. But for a geometric sequence, it can. Because with a geometric sequence, the terms don't always have to get bigger and bigger. They can get smaller and smaller and approach zero. That's the key. If you have a sequence where the terms are approaching zero, like 1/2, 1/4, 1/8, 1/16, they're getting smaller and smaller and smaller each time, that's the kind of sequence we could look at. So here's the notation using sigma for an infinite series. Not really much different from yesterday. Your starting point, in this case the index starts at 1, but now it stops at infinity. So there's no fixed value on the top. And when we expand it, we have the first term, the second term, the third term, fourth term, dot, 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 all the way up to the nth term, but now the nth term isn't the last one. There's the nth plus 1 term, the nth plus 2 term, nth plus 3 term. It just keeps going on forever. So that's the notation for how you could write an infinite series expanded out. So obviously we can't add an infinite amount of terms by hand. It would kind of take a little while. So we need a better way than adding up infinitely many things. All right? So we're going to try to come up with a formula. And we can basically use the formula we came up yesterday that we used for a finite series. So we'll get to that in a little bit. Okay, we got to make a small adjustment to it, but we can pretty much use it. So let's kind of go back and think about something we did quite a while ago. It was a name for a line. We usually made it a dotted line, or it could have been curved, that something got closer and closer and closer to, but it never reached it. Anybody remember what that line was called? When you draw it and your graph gets closer to it? An asymptote. That's kind of how you can think of an infinite sum. Okay? You keep adding up and your sum is going to get closer and closer and closer, but it's never actually going to reach it. So, the first approach we're going to do is going to be more visual. Then I'll show you how you can just use a formula and you don't need to do anything visual at all. So, if you can find some number such that the graph y equals that number is a horizontal asymptote for your sequence of partial sums. So, let's say when you added up, just going to make it up. When you added up the first 1 terms in the sequence, you got 1. When you added up the first 2 terms, you got 1.5. The first 3 terms, you got 1.75. The first 10 terms, you got 1.99. The first 100 terms, you got 1.9999999. Basically, in that problem, y equals 2 would be a horizontal asymptote. because it's what your sums are getting closer and closer to, but never actually reaching it. Okay. So if that particular number is a horizontal asymptote for the sequence of partial sums, then we say that our sequence of partial sums is converging to that number. In the example I just gave, we would say it was converging to 2. We'll talk about what happens. There's a different word we use if it's not converging. Like if we're adding up more and more terms, let's say you add up terms and the first term is 1, and then you add up the first 10 terms and you get 100. Then you add up the first 1,000 terms and you get 500. Well, it's not really going anywhere. It's just getting bigger and bigger as you add more and more. That's a little different. All right. And of course, this is all happening as the number of terms approaches infinity, okay, as you add more and more. Practically speaking, most sequences that converge, or series that converge, they converge very quickly. You could add up the first 6 or 7 terms, and you can already tell what it's going to approach. It's not like you need to add up the first 200 terms to see what's going on. You can really see this pretty quick. And that particular number that it's approaching, that's the horizontal asymptote, that's what we would say the sum is. So technically, does an infinite series ever reach the sum? Not really. Because you can't add up infinitely many things. It can approach it, and it can get closer and closer, but it can never really equal it. Except at infinity, which isn't really enough. Any questions on that idea? So that's what we're going to kind of use as a starting point to add up infinitely many terms. We'll use the formula we had yesterday, but instead of just adding up the first 2 terms or 3 terms, we'll use the formula in the graphing calculator to add up the first 50 terms. Okay? And that'll be a good indication of infinity, okay, seeing what happens. Okay, so again, an infinite series isn't really a sum. You're looking at the partial sum for a ton of numbers, like the first 100 or the first 1,000. And that's kind of our indicator of what would happen at infinity. So we're looking way, way up in the sequence of partial sums. Okay, and again, in reality, you don't even need to look that far. Usually by the 10th partial sum, you can predict the pattern. Any questions on that? All right. So for a geometric series, okay, that's what it would look like in sigma notation. You would have your first term times r to the k minus 1. That would be your formula. So in a real problem, it would be something like this. 2 times 1/3 to the k minus 1. So there's your geometric formula. And then if you expand it out, that's just what I've done here. K is 1. You get r to the 0th power, which cancels out, and you're just left with a sub 1. When k is 2, you get 2 minus 1 is 1. R to the 1st times a sub 1. And that's what I wrote right there. So I just expanded this out from the sigma notation so you could see it. Okay, but the key when you look at it, your first term is sitting right there, and your r is the base on the exponent. So let's look at this one. So they want us to add up every number in this sequence from 1 to infinity, and the sequence is 2 times 1/3 to the k minus 1. Okay, let's just write out a couple terms in this sequence, just so we can kind of see what's happening. If you let k equal 1 and plug it in, what would be your first term in the sequence? Yep.
2.
2. Plus, okay? With just the first term, bless you, I can't tell you what's happening at all. I need to see some more to figure this out. What if you let k equal 2? What would be your next term you would add? And we can keep it as a fraction. Oh, Tyler?
2/3.
2/3, yep. Okay, so that's smaller than 2, but again, with just that little information, I still can't really tell what's going on. Let's do a couple more. What if you let k equal 3? What would be the next term? Abby? 2/9. You're multiplying by 1/3 each time. So the next term after that would be 9 times 3, 2/27. Okay, now I can start to see what's happening. What's happening to each term in that series as we go further and further out? Oh, Brooke?
It's getting smaller.
It's getting smaller. What's it approaching? Not the actual sum, but just the individual terms in the sum.
0.
Yeah, the individual terms are approaching 0. So what that means is at some point, the terms are going to get so small, they don't even matter anymore. Okay? So instead of doing this out like this, let's use the formula that we had from yesterday, okay, which I've already filled it in. So to find a partial sum, it's a sub 1 times 1 minus r to the n, all over 1 minus r. So I'm just using the formula from yesterday, and I let n equal 4 for s sub 4. Now, since we did out the first 4 terms, I could actually check this. The first 4 terms should add up to 2.96 using this formula, okay, if you type it in. But let's check it. We've got 2 plus 2/3 plus 2/9 plus 2/27. I should probably keep parentheses around all of them. And you get 2.96. So this automatically adds up the first 4 terms for you without having to do it out. Because I'm not going to do any more terms out, but I want to know the 5th and the 6th partial sum. So the 5th partial sum, a sub 1 times 1 minus r to the n, all over 1 minus r. Well, if you were to add the next term onto our series and add it in, you'd get 2.98. So, at least for me, after the first 5 terms, I can already tell what it's getting close to. What does it look like this is getting closer and closer to? Then 3. Yeah, it's getting pretty close to 3. In fact, by the time you add up the first 6 terms, you're already at 2.99. And that's just the first 6. Never mind if you did the first 50. In fact, if you did the first 50, we probably don't have a calculator in here that could do enough decimal places, enough 2.99999. It probably would just say 3, okay, because it would run out of decimals. All right. It's getting pretty close to 3. So, any questions on it? How we went through that, and then how we could kind of reason out, well, if you wanted to get s sub infinity, basically, well, you could actually say it would equal 3 at infinity. Okay, so that's what you would get if you added up every single term in that sequence and continued it out forever. Okay, we'll look at that visually in a little bit. 1, because I want you to see it visually. 2, because it's a little hard to type all that into the calculator. You got to have your parentheses just right. Okay, so let's visualize what we just did. So here's our formula. And in order to type this in, remember I can't use n. I know in the formula I said r to the n, but remember the graphing calculator, you have to use x for the variable. Now, x represents how many terms you want to add up. Do you want to add up the first 2, the first 5, the first 20? So why did I say to focus on positive integer values for x? Why can't x be 3.5? I mean, numerically, you will get an answer if you go to your table, put in 3.5 for x. It'll give you a value for y, but it has no meaning in this at all. Yeah.
You can't have a place of 3.5. You can't have like a spot in the sequence.
Yeah, there's a third spot and there's a fourth spot. You can either add the first 3 terms or you can add the first 4 terms. You can't add the first 3.5 terms. There's no such thing. So that's why when we graph it, we're just going to focus when we look at our table on positive integer values. Okay, don't look at decimals. I wish there was a way on the calculator you could go into like the mode and set the domain to be positive integers. And there might be, but I'm not sure. All right, so our first term was 2, and r is 1/3. Okay, so we have to fill that in. So r is 2. I'm going to put double parentheses, because I think I'll need them. 1 minus r to the x. All right, so I close the parenthesis for my 1/3 fraction. I'm going to close the parenthesis for my numerator. But this 2 is still on the outside of everything, which is the way I want it. Divided by. Let's do this a little easier. What's 1 minus 1/3? Yeah. 2/3. So that's just easier, so I don't need another set of parentheses. So there's my denominator, and there is closing the first parenthesis I opened. That should work. Okay, we'll know if I go to the table and if we don't get the right answers. Okay, if you add up the first term in that sequence, you get 2. If you add up the first 2 terms, it should be 2.6 repeating. Yep. And then if you add up the first 4 terms, we already did that, 2.96. If you add up the first 6 terms, 2.9959. Okay, so I typed it incorrect. Now, let me jump to like 12 terms. So it says 3, but is it really 3? No, it's just approaching it. And sometimes if you highlight it, yeah, there's still enough decimals that it can still show you that it's not 3. But eventually, like if you add up the first 25 terms, now it just says 3. Okay, we've run out of space for 2.9s. Okay, but remember, it never really hits 3. Yeah. All right, so let's just take a look at what that looks like as a graph. Okay. What I should really do is set my window to positive. Don't look at negatives, because negatives don't make sense at all. All right, so let's look at that. And that's what our sequence of partial sums look like. If you add up the first term, you get 2. Okay. If you add up the first 2 terms, you get 2.6. Technically, those shouldn't be connected because there's nothing in between adding up the first term and the second term. Okay. It really should just look like dots. And the dots are getting closer and closer to 3. Till eventually I run out of resolution and it looks like the line is at 3. What you could do is you could put the line at 3 and then you could see it yourself. 3 is a horizontal asymptote. Again, it looks like it's right on top of it, but it really shouldn't be. So any questions on that? So graphic calculator is a nice way if you want to check for an infinite sum. You just type it in, use your table. Makes it pretty easy. Let's see. All right, so we did it graphically. Let's look at this one. What's your, before we even do anything, what's your starting value here? You're starting your first term. Oh, Destiny. Four. Yeah, the first term is 4. And then to get each term after that, what are we multiplying by each time?
3.
3. So my next term that I would add would be 12. How about the term after that? 36. What's happening to the terms here if I continued them out? Oh, Cassandra? Okay, you're multiplying them by 3, so what's happening to each term? I know specifically we're multiplying it by 3, so that means each term is getting bigger. So what does that mean about the sum? If you add up a bunch of numbers that are just going to get bigger and bigger forever, what would they add up to? Okay, infinity. There wouldn't be a numerical answer. So if we try this, let's just change our formula. The first term is 4, and now r is 3. So 4 times 1 minus r to the n, all over 1 minus r. Well, r is 3, so 1 minus 3, negative 2. Okay. I don't need as many parentheses now, but I just left them because we had fractions before. All right, so let's check it. If I add up just the first term, it should be 4. The first 2 terms should be 16. 4, 16. And then the first 3 terms, 4 plus 12 plus 36. We didn't do that one, but let's just check and make sure it works. So the first 3 terms add up to 52, and that's what 4 plus 12 plus 36 is, 52. So as you can see from the table, what's happening is it's just getting bigger and bigger. Okay, the sum isn't approaching anything. Eventually it's going to use scientific notation because it's going to get so big. So the answer here is, when you say find the sum, there is no sum. So now, a better way to write that is to say that this is divergent. So this particular sum diverges, or you could just say divergent. So the way you'd probably see a question on the test is I would give you a sum, I'd give you a problem, and I'd say, determine whether the following is convergent or divergent. If it converges, tell me what it converges to. Now, a mistake that people always make when I ask that question is there's a difference between, let me go back here, what the terms are converging to. Okay, the individual terms are approaching 0, but that's not what the sum of the terms is approaching. The sum of the terms is approaching 3. Right? And that's usually what I'm interested in. I know the terms are approaching 0, but what is the sum of them approaching? Okay, so don't mix that up on the test. Here, you wouldn't be able to say what they're approaching. You would just say divergent, and you'd be done. So, sometimes a geometric series can converge. That's the first one we did. Sometimes it can diverge. That's the other one we just did. So whether it converges or diverges, we've got to come up with a method for figuring that out. Okay, I don't even want to waste time if it diverges. I just want to know right away. And there is a way you can tell. Can anybody tell how this one on the right diverges and why the one on the left converges? What's the difference between them? Yeah?
R is a fraction in the one on the left, and then it's a whole number in the one on the right.
Yeah, it all depends what you're multiplying by each time. Are you multiplying by something that's going to make each term smaller than the one before it, like half as big or a third as big? Or are you multiplying by something that's going to make each term bigger than the one before it, like doubling, tripling, something like that? So in the book, I think they kind of have you go through just practicing, well, what if you let r equal 0.8, 0.9, 1.1, and 1.2? You can see what's happening. What would happen with the first two? I don't think we need to go through it and graph it. But if r was 0.8, or 0.9, what would happen?
It would converge.
Yeah, these would both converge. Now, A would converge faster than B. We're not really getting into the rate of convergence. You could talk about that. The closer R is to 0, the faster it converges. Think if you take a tenth of a number over and over, or you take half of a number over and over. Well, if you take a tenth, it's going to get smaller faster, okay, which means it will converge faster. What's going to happen in those two cases if R is 1.1 or 1.2? Devin?
They're going to diverge.
Yeah, that one's going to diverge. 1.2 is going to cause it to diverge faster than 1.1. Think if your first term was 5, and you multiply by 1.1 10 times. You get 2, 3, 4, 5, 6, 7, 8, 9, 10. So you multiply by 1.1 10 times, you're at about 11.8. Now do the same thing, but multiply by 1.2 10 times. So 2, 3, 4, 5, 6, 7, 8, 9, 10. Much, much bigger. Okay, it diverged faster. So the bigger R is, the faster it diverges. Okay, any questions on that? All right, so now we can kind of summarize that by saying that if the absolute value of R is less than 1, then the infinite geometric series converges. Now, I said absolute value because technically R could be negative a half. That would be okay. What would happen in that case is you would get a sequence that oscillates positive, negative, but it would still be approaching 0. So you might have something like positive 2, negative 1, positive a half, negative a fourth, positive an eighth, negative 16th. It would oscillate back and forth. Now, let's see what it would converge to. Can someone remind me, what's the formula that we use for finding the sum of a finite geometric sequence? The one we had yesterday. Yep.
A sub 1 times 1 minus R to the n over 1 minus R.
All right. So I want to focus on what's going to happen right there. If this is going to converge, we know that R, the absolute value of R, is less than 1. What if you take a number less than 1 and raise it to a really big power? What happens to it? Take any number that's less than 1, like a half. Raise a half to the millionth power. What do you basically get?
Small.
A very small number. And what's that small number going to approach?
0.
0. Right? If you take half raised to even just the 10th power, it's half of a half of a half of a half 10 times. It's pretty small. So this approaches 0 if we meet that condition and n gets bigger and bigger. So what I just circled will approach 0 if the absolute value of R is less than 1 and n heads towards infinity. So really, when n gets really big, we can just pretend that that term doesn't even exist. This is going to become 0. So we get a sub 1 times, what's 1 minus 0? 1 over 1 minus R. And we could multiply that out. Just think of a sub 1 as a fraction. Multiply straight across. A sub 1 over 1 minus R. So for an infinite geometric series, we just did it all out. I'm not going to write it again. Just copy down what I just went through right here. This is what happens. So that's the sum of an infinite geometric series that converges. Now, you can use that formula on something that diverges, and you'll get a number. But that number, for our purposes, doesn't mean anything at all. So it's not like you get an error if you try to use this formula when it diverges. It's just, it's totally wrong. It has no meaning. So only use that formula when it converges. Okay. Does everyone have that formula? A sub 1 divided by 1 minus r. So, I'm not sure what you think, but I think that's an easier formula than yesterday. You might think, well, when you start doing things that are infinite, it gets harder. I think the formula is easier. Okay, so let's look at this one. Now, on the test, this would say determine if the following is convergent or divergent. I'm already telling you to find the sum, so it does converge. But can anybody tell me how I know that that one would converge?
R is half.
R is a half, and what does R have to be to converge?
The absolute value has to be below 1.
Right, it has, so basically R has to be between -1 and 1, and it is. So let's figure out what it converges to. So the nth partial sum, or actually, we're not even doing nth, the infinite partial sum, equals, okay, we have a fraction. Abby, what goes on the top of it? Yep, so 5. And then in the bottom, Brooke, what do I divide by?
10. Oh, wait.
Okay, what goes in the bottom, Devin?
-1/2.
All right, can you just tell me how you get that?
1 minus r, so 1 minus 1/2.
1 minus 1/2. And what's 1 minus a half?
-1/2. Or, no, 1/2.
1/2. So we get 5 divided by a half. And 5 divided by a half is how much? Yep.
10.
10. Some people say 2. Remember, that's not 5 divided, or some people say like 2.5. It's not 5 divided by 2. Okay, so just be careful. 5 divided by a half gives you 10. And that's it. So if you were to add that up, every single term to infinity, it would add up, or it would approach 10. Okay, question on that one? Okay, so that pretty much finishes up the second half of section 11.2. So I think the infinite part is actually, I don't know, I think it's a little shorter, a little quicker than the finite part. All right. So just to kind of give you kind of an introduction of what's going to happen tomorrow, so I don't have to do it then. If you had something like that and you wanted to do it out, well, how do you do that out? Because some teachers call it something. Because you can't just write x squared plus 4. That's totally wrong. Yeah. You FOIL. So you have to write x plus 2 times x plus 2, and then FOIL it all out. And that's the answer. Not too bad. Well, what if I had x plus 2 to the 12th? Well, now I've got to write x plus 2 12 times and FOIL everything out. It's not hard, but there's just so many steps, probably going to make a mistake somewhere. So in section 11.3, we learn a very fast way to do that. Okay, very, very fast way. So that's what we'll look at tomorrow. And it also ties into probability a little bit, combinations, and we'll talk a little about factorials. People seen that symbol before? So we'll talk about that a little bit. But it's kind of its own separate thing. And we'll look at that tomorrow. Bless you. All right, so the homework is on 601. Okay, you got about 30 minutes to start it, so please use the time to try to get some of that done. But it's 21, 22, 29, 30, 32, 33 to 35, 37 to 39, and 42 to 45. Okay, don't forget, I will be after school tomorrow for extra help. Okay, the final, I gave you the review sheet for that, and that is 2 weeks from tomorrow. Okay, it's next academic Thursday, okay, which is also another MCAS